Hello, everyone. Welcome to the webinar, the QuEra's webinar about resilient networks, quantum solutions for optical fiber optimization and telecommunication. So why don't we get started? First, welcome again. My name is Yuval Boger. I'm Chief Commercial Officer for QuEra. I'm responsible for QuEra's sales and marketing globally. And I have three distinguished guests with me today. Antonio del Corral, CEO of CINFO. Hey, Antonio.
Hello, how are you?
Excellent. Thank you. Jan Trautmann, Principal Engineer at Kipu Quantum. Hey, Jan.
Hey.
And my colleague, Jonathan Wurtz, Senior Research Scientist at QuEra Computing. Hey, Jonathan. Thanks for making the time today.
Yes, of course.
We are going to do a few things today. So in terms of the overall agenda, I'll start with a few words about QuEra. Antonio will describe the problem that they wanted to explore together with Kipu. Jonathan will provide some background on optimization using neutral atoms. Jan will present the algorithm and the results that Kipu received and how they addressed the problem presented by Antonio. And then all of us will be happy to answer any questions. How does that sound? Wonderful. So about QuEra. QuEra is the leader in neutral atom computers. We believe that neutral atoms is the best modality to create quantum computers. There are many reasons for that. Neutral atom computers operate at room temperature. They can scale to a very large number of qubits on a single machine without the need for optical interconnects. They are neutral, meaning the atoms are both neutral and the atoms are natural, meaning there are no manufacturing defects in the qubits themselves. And of course, neutral atom computers have this fantastic capability of all-to-all connectivity, where every atom could be moved to interact with every other atom, and that creates significant advantages both in efficient algorithms and in quantum error correction. And we believe that not only neutral atoms is the best way to create quantum computers, but QuEra is the leader in neutral atoms. QuEra, in fact, is the only company with publicly accessible neutral atom computer, available 130 hours a week on Amazon Bracket. We are headquartered in Boston, close to Harvard and MIT, and it's not just a geographical proximity, it's also an ideological proximity in the sense that our technology was started at Harvard and MIT. Our founders were from Harvard and MIT, and we continue to enjoy very close collaborations with these two world-class institutions. QuEra today delivers on-premise quantum computers. We announced recently deals to deliver a computer to Japan and also a machine to the UK. And we also provide cloud access to our computers. And we're hiring. We're about 60 people today. We expect to be 100 people or so in the not-too-distant future. So have a look at our careers page on QuEra.com, and we'd love to have you join our amazing team. As far as the computers that we offer, so today we offer an analog computer, and Jonathan will talk more about that, called Aquila. It was launched on November of 22 on Amazon Bracket. It has 256 qubits. And earlier this year, after a breakthrough research that was published from Harvard and MIT and QuEra and others, we announced a roadmap for error-corrected quantum computers. This year, we expect to have a machine with at least 10 logical qubits. These are 10 error-corrected qubits, or 10 qubits that support error detection and some correction. That should be followed in 2025 by a machine that has more than 3,000 physical qubits and at least 30 logical qubits. And also in 2026, a machine that has more than 10,000 physical qubits and about 100 or so logical qubits. First, of course, it's not 2026 yet, and the number of logical qubits also depends on the encoding you choose. But the key thing is that somewhere between 25 and 26, somewhere between 30 and 100 logical qubits, we expect quantum computers to exceed the capabilities of classical machines in the sense that you cannot simulate a computer with 100 perfect qubits on a classical machine. So we're at the precipice of some really exciting times. And we were heartened to see the response from the reaction from Professor Preskill, the Richard Feynman Professor of Physics at Caltech, that looked at our roadmap and says, ambitious but not crazy. And just to close this section about QuEra, there are 3 ways you can work with us. We deliver machines on premises to integrate with HPC centers. We provide premium access, both access through Amazon Bracket as well as access directly through QuEra, where you can enjoy both the computers as well the support of scientists like Jonathan and his colleagues. And we also engage in joint development with customers, with strategic customers, to develop killer applications that take advantage of our upcoming error-corrected computers. And with that, Antonio, maybe you could take a few moments to talk about CINFO and also describe the problem that you wanted to look at.
Okay, thank you very much, Yuval, and thank you very much for inviting us to stay with you in this webinar. You're watching my screen.
It's coming up.
Coming on. Well, just one-page summary about us. We are a Spanish company working in the telecommunication environment. Actually, we are a spin-off of a telco company, which was purchased by another one, and merged together into what is the biggest telco operator in Spain, which are our customers and also our friends. And we work usually in telco and pay TV backends, 5G APIs, and also in cloud video generation and cloud TV production assisted by artificial intelligence. Well, we are very much in contact with the telco environment. We know their problems. They are our customers. So we suggested to them to start introducing quantum technology into their backend systems. And they gave us a positive note to the idea. And also they suggested, why don't you propose a use case for the quantum technology? Okay, this is the map of Spain. Our customer, in this case, which is Mas Orange, they have a big network here in this region. They have another network in this another region, another here. Then they have a national network named MásMóvil covering the whole of Spain. But in parallel, they have another network called Yoigo, not merged with MásMóvil 1, and still they have Orange backbone national network and distribution, and all together they are merging now all these kind of networks, different networks, into a single one. So they have a big problem of network optimization, network decision in terms of configurations, and they are looking for alternatives overall in the case of problems, because when crises arise and network disasters happen every day and are managed routinely, but you know that with all these geopolitical threats, major outages are a real scenario. And when problems happen in the network, it's very difficult to stay calm and very difficult to take decisions, because everything is chaos and all is predictable chaos, and they want to have tools for this kind of situation. So the target for the project is to have pre-calculated thousands of network configurations, so at a crisis time, analysis time is minimized. So what they expect from quantum technology? They expect that when we define many network situations, we have many network problems, not only cybersecurity, but national disasters, or even, geopolitical problems where the part of the network is affected, and quantum technology is able to provide a recipe for this kind of situation. And this is the sample backbone, also simple, you will know why. They have given to us to model inside quantum computers. This is not the whole thing in network configuration. This is just one of the original backbones connecting only the headends in a given region. And remember, they have this region, another region, several national ones, and they are merging all this together. This model, which has not only links, it has also network equipment, capabilities, traffic, and different types of network traffic inside it, well, is too complex as of today for quantum computers. We wanted in the project to learn how to model this kind of telco backbone inside a quantum architecture, and we had to do it. We, during the project, identified what quantum algorithms can represent network links, network node, network capacities, and traffic levels. We wanted to design an algorithm that can represent the concept of network resiliency. So if this part of the network is affected, what is the system telling me that I have to do to minimize affection to customer segments? And we wanted also during the project to learn how to use the output of the algorithm in a real emergency case. What is how to store the output of the quantum computer, translate it back into network configurations, and being able to apply it in a real case when there is a real emergency. And well, to this, we designed a toy model, the biggest network model that we could fit into a quantum architecture, and also simple enough for us to predict what the results were and to be able to check against classical and computation the reality. And well, this is the model we inserted into the algorithm. This model has different types of links, different type of equipments, and well, different redundancies between nodes representing headends. Well, our model, we thought it was simple enough, but also complex enough. It has 46 network nodes. It was modeled in different architectures and mainly over a QuEra quantum computer. It fitted inside the quantum architecture we had available well in the last autumn. It was when we ran this project. And it does not solve, of course, the whole thing, but it gave us the understanding that this kind of technology can really provide a solution in terms of speed and calculating all the possible different affections to the network. So provides one step towards a real solution that can be put into production. It also delivered good results. We tested many different kinds of network problems inside this model. It always gave the result we expected. And our expectation is that every year we will enhance the model until it really resembles a realistic quantum backbone network configuration and is able to calculate all these myriads of different affections that we expect to be the final output of the project.
Antonio, you mentioned that the model has 46 nodes. How large is the real network? How far are we from doing something that would truly be useful?
Well, I think we are about 10% with this toy model of a regional network, which is, by the way, the standard case. You see, national backbones are really a part of several regional networks. So when you model a regional one and another regional one, maybe you are close to the whole thing.
And how did you verify that the quantum solutions were correct? Do you have an existing classical model that does that, or is it basically the expertise of your network engineers?
Well, we don't have a classical software model, let's say a digital twin of the network, but we network engineers, they have a number of rules and thumbs ups and thumbs down rules, and everything coming from the project was a thumbs up solution that they will use in a real case. So they trusted quite the output. It's true that they don't have a classical simulation. it was considered too complicated to create a classical software that simulates really a network model.
And the last question at this phase, I'm curious, you mentioned that you're running thousands of different scenarios and storing the results. Would you expect that to be the case in production, or would you expect more of a real-time solution? A network goes down or network node goes down, you submit it to the quantum computer and get up-to-date results?
Well, I think that, I interviewed several network managers and directors, and finally the global CTO of MassMobile. They never expect to use a quantum computer in a real crisis. They expect to have a service using quantum technology, providing many simulations, because the network is continually updated. So the simulation you did last month is not real today. So you have to be continuously running simulations against the quantum computer and have the recipes ready, and they use the recipe that most resembles your real problem. But at crisis time, they don't have the time to model what is going on and go into a quantum computer.
Understood. Very well. So before we go to Jan to talk about the specific solution, Jonathan, maybe you can give an overview of how to do optimization using neutral atom computers and what the advantages are.
Yes, of course. Good. All right. So hi, I'm Jonathan. I'm here at QuEra on the algorithms and applications team, working on, of course, algorithms and applications, mainly to do with our near and upcoming quantum hardware. And today I'll talk a little bit more about our current generation quantum computer, Aquila, as well as some applications and algorithms that we've been thinking about in terms of optimization. Good. So as Yuval described the company, I will describe our first flagship computer, Aquila, which is an analog mode quantum computer available through the cloud through Amazon Braket. It has up to 256 neutral atom qubits in an analog mode, which I'll describe a little bit more on the next slide, which I believe is the largest publicly accessible computer in the world. Now, there are many different applications. I guess the three key ones are simulation, optimization, and machine learning. Today, I'll spend a few more details on optimization. And this machine is quite interesting because as well as being a very powerful machine, it also has many interesting both industrial and academic applications, and has already spawned many scientific publications. So, as I described in the previous slide, Aquila is an analog mode quantum computer. And an analog mode computer is slightly different from the conventional gate-based quantum computer that most people may be used to. So instead of executing a series of quantum gates to build up entanglement and correlations in your system, instead what you do is you execute time-dependent Hamiltonian dynamics of some system of qubits. I guess it's not a QuEra computing slide talk if we don't present the Hamiltonian in the second slide. So here it is. So our Hamiltonian is an Ising-like Hamiltonian. So we have some transverse field term, which jumps between our ground state and our excited state, which creates superposition. And we also have some interaction term, which creates entanglement. And the idea here is, unlike this sort of gate-based mode, you have sort of an everybody gate. So your time dynamics very quickly grow entanglement and correlation through the system. Now, what we can do is we can program our device by specifying positions of up to 256 qubits. So for example, this is our machine, and you can sort of pretend that we zoom in here on being able to basically arbitrarily position our qubits in our array. So this is actually a picture of each dot here as an individual qubit in our array, outlining the coastlines of the world. And then you encode your problem in your positions of atoms, and you also define some time-dependent waveforms, and you're able to submit these jobs to the Amazon Braket cloud. And this device is useful for things like non-equilibrium dynamics, adiabatic state preparation, and quantum quenches. And now, while adiabatic state preparation is a thing that this computer can do, I should emphasize that it's not the only thing that this computer can do. And actually, a lot of interesting applications end up being with this sort of non-equilibrium coherent quantum dynamics in mind. Good. So we've identified 3 key problems that our computer can solve. The first is machine learning. So we have this idea called reservoir computing, which is useful for things like classification, regression, and prediction, which uses exactly this non-equilibrium dynamics mode of this analog mode device in order to do machine learning tasks. Second is optimization, which I'll detail a little bit more. But we have our favorite problem, which is a maximum independent set, which is the defined as a graph problem such that the subset of vertices such that no 2 vertices are adjacent on the graph. And then finally is simulation. So this is, for example, if you want to simulate a Rydberg atom Hamiltonian, we're really great at that, but we're also able to simulate things close by to the neutral atom Hamiltonian, such as lattice gauge theories, phases of matter, quantum dynamics, and so forth. So as a simple example of using our device, let's consider an example of store placement. So suppose we have some set of stores in Manhattan, say coffee shops, and we want to find the maximum number of coffee shops such that no 2 coffee shops are close by to each other. So basically, if you put a coffee shop here, then you're not able to put a coffee shop here because they're too close and they're connected by an edge. Now, this problem is the maximum independent set problem, because basically this is, you want the largest set of vertices such that no 2 vertices are adjacent to each other. Now, what we're able to do is we're able to define this problem by placing our atoms in arbitrary positions, right? So now you can see this is the analog of this problem by placing all the atoms. And then we could do some quantum dynamics to find some approximate or optimal solution by measuring the atoms and basically inferring the solution from either the ground state or the excited state of each atom. Now, the independent set problem is nice because, in fact, this very naturally maps onto our hardware through this notion of something called the Rydberg blockade, which is basically the energy, the strong interaction energy of our Hamiltonian naturally maps onto the independent set constraint of an objective. And in fact, there's a landmark demonstration of solving these maximum independent set problems. And this is this paper up here, I guess this paper here, on solving maximum independent set on a certain kind of graph called King subgraphs, which look like this. And we can, in fact, see that we're able to variationally optimize these protocols and see that there is possibly even a quadratic speed up in terms of convergence to solution over existing classical algorithms. And this tells us that, in fact, this device is able to, at least in theory, solve a certain subset of problems, possibly with a greater effectiveness than an equivalent classical algorithm. Now, the challenge, of course, is that not every problem is independent set. And this leads us to some of our more recent work called non-native hybrid algorithms. And we have an archive link down here if you're curious to learn more. And the question is as follows. What if the problem solution does not map to a ground state, right? So for example, in our independent set example, the ground state was the solution. So we could do an adiabatic protocol to prepare the ground state and then measure to find our solution. Now, this non-native hybrid algorithms approach instead uses a key insight that our measurement outcomes are no longer directly linked to our problem solutions. And instead, this is we use our device as a coprocessor compute solutions. So as an example, we might consider the max k-cut problem, which is like max cut but instead of 2 colors to k colors. And then here we can use a quench dynamics in order in order to solve this problem, possibly with a greater effectiveness than a classical only version of that algorithm. And this tells us that, like, at least in principle, we're able to use both quantum and classical resources to get better solutions to these optimization problems. And in fact, this notion of hybrid algorithms is key if we want to get beyond these theoretical pictures of just, these simple and independent sets to more complicated problems, like, for example, backbone optimization and other interesting multi-scale problems. So with that, maybe I'll just mention one last thing, which I'm very excited about, and I think all of us here at QuEra are, which is that while everything here we discussed was on analog mode, which is basically this all-to-all Hamiltonian dynamics, this is a non-universal mode of computation. However, we are also concentrating on both digital mode, so gate-based mode, as well as logical mode computation. And this has the similar power of neutral atoms, where we can have, say, hundreds of qubits, say 256 now gate-based qubits, but also enabled by an all-to-all connectivity based off of a mid-circuit atom moving architecture. And of course, with this also comes the great power of logical and error-corrected qubits as well. Good. So with that, I will pass it over to Jan to describe a little bit more of the specific implementation of today.
And Jonathan, while Jan is loading the presentation, are there code samples online where people could download and perhaps experiment with running these type of optimization problems?
Yes, this is a great point. So most of our code is demonstrated is using our SDK called Blockade. And if you go to our GitHub page, I guess Yuval, maybe you can link it. If you go to our GitHub page, this will include many starter examples using Blockade. And in fact, it should be the case that all of the example that I showed here on Max K-Cut actually should be, you should be able to actually generate that exact same plot using that example code. So it is designed as a base for further exploration.
And just for those that are unfamiliar, Blockade is our free and open source development environment where you could simulate both on your local computer as well as on clouds or GPU clusters. But then one of the fabulous features of Blockade is that you can then submit from Blockade directly to the Amazon Braket cloud service. So once you're comfortable with how the algorithm operates in a simulation, you could run it on the real machine. Jan, the floor is yours.
Thanks a lot. Thanks a lot, Antonio, for preparing the nice first overview of the problem. And thank you, Jonathan, for this nice overview of the QuEra hardware. Now let's have a bit deeper look into the problem that we tackled and how to use the hardware for that. So for this project, 4 parties teamed up. So we have Maslovil, CINFO, QuEra, and Kipu, where Maslovil, as European leader in Telco, provided the problem. CINFO did the modeling of the network problem, and we as Kipu did the development of the algorithm that we then ran on the QuEra hardware. Before we jump a bit deeper, I would like to give you a brief overview of what Kipu is actually doing. Kipu is a German-based software startup that develops algorithms for quantum computers. The solutions we are developing and providing are based on our algorithmic compression technology that is based on counter-diabatic terms. Our algorithms are also application-specific and hardware-specific. With these 3 ingredients, we believe, and we are very confident, that we can provide a path towards quantum advantage without the strict need of error correction. When we compare our algorithms against state-of-the-art quantum solutions, we see that we can beat competing algorithms by orders of magnitude. For example, we have seen that one of our algorithms has a 500 times shorter time to solution, while another one was also able to increase the success probability by 600 times. We were also able to demonstrate 100 times better results. I would like to note here that all these comparisons we did and these values we extracted were done actually hardware and publicly available hardware. Our items that we are developing are also done for several verticals and use cases, where today we'll be mostly focusing network optimization for telco, but we are also working on protein folding for pharma and biotech, portfolio optimization for finance, combinatorial optimization for logistics, and we are also looking into electronic structure calculations and simulations for chemistry and pharma. So now let's dive a bit deeper into network optimization. The first question that may arise is actually what makes one network better than the other one and how to optimize this. Therefore, let's take a look at an example where we have here on the left some cities or regions connected by fiber optics and networks. And we would like now to find a measure of how resilient this network is if one node of these systems fails here. So for example, if this node here in the middle and top fails, we can see that this network is still functioning because all other cities and nodes are still connected. So therefore, this network in this kind of sense is resilient against this failure because we have here this redundancy in the connectivity. But now what happens if, for example, the central node here fails? We can see that the network would be split into two pieces because we do not have any redundancy here. And now the question arises, how can we characterize this redundancy and how can we characterize resilience? Our approach there was to actually map this network to the neutral atoms and calculate the maximum independent set. So for example, if we would map now this problem here onto neutral atoms, we would obtain the graph here in the center, and then we can calculate the maximum independent set, which gives us this solution here. And we now use the size of this maximum independent set to quantify the resilience of the network and identify redundancy gaps. So how can we actually do this? To answer this question, I would like to take a look at two extreme cases where we have here on the left a sparsely connected network and on the right here a very densely connected network. So when we now solve the maximum independent set problem of the network on the left, we can see that this actually the size of the independent set is actually 8 nodes, and we now use the size of this independent set to calculate the resilience measure. So therefore, we are taking the ratio between MIS size and the total number of nodes. And as we can see here, this network has a pretty low resilience because it has a large independent set, and this reflects that when the center node fails, the full network will break down, and we do not have any redundancy. In contrast, we have here on the right the densely connected system, where we only then obtain independent set size of 1, which reflects that we have a large redundancy in the system and characterizes a good resilience against failures of this. Because this measure also depends on the ratio of MIS size against the number of nodes, the scale of this measure also depends on the network size, where a large network is more likely to face issues. So now let's take a look at the approach of a real problem, how this could look like. So on the left, we have the simplified backbone that where the model Antonio already presented before. And this backbone contains here several regions, which are marked with these cities, and also parts of subnetworks, which are here these tiny houses. And in order to now solve this full problem, we could not fit the full connectivity into a single atomic approach or mapping it to a single atom distribution on the system. So therefore, we divided the problem into subparts, where we first characterized the backbone by itself, and then also took a look at the subnetwork structure independently of each other. If we now take a look at the simplified backbone, we have separated the parts here, and the subnetwork structure we just modeled as one node here in these rings. And by doing this, we map then the network onto neutral atoms, where most of the atoms, like for example the central part here, is reflected by individual atoms here, but we also had to introduce additional gadgets or additional atoms to reflect the full connectivity in the system and to not interfere and to map it to unit disk graphs. We then actually solved the MIS problem of these neutral atoms here on the device, obtained the solution, and then by doing some post-processing, we actually map back the MIS solution onto the real network, as you can see here on the right. And there we obtain then, by taking the size of the independent set, we could actually calculate here the resilience measure of 0.6, which is actually pretty good because this network it contains 18 nodes, and it still has a quite high measure of resilience. This is mostly the effect because we have here this nice ring structure. So if something in the ring, for example, here would fail, we would still get the connectivity through the system. And we also have a large redundancy in the central nodes here, that even if the center fails, we still have a high connectivity and redundancy, which also makes perfect sense because this is the most important part of the network. So the backbone has to be very resilient, and it's also not so easy to change. In addition, we also took a look at the smaller subsystems that we have in the full network, where we mapped each of the subnetworks to neutral atom hardware and use it to find the max independent set independently of the systems here again. And as you can see, the subnetworks all have a different kind of structure, where some have a very high resilience, as for example this one, while others have a rather low one, or even a quite low one network structure. And this is due to the fact that, for example, here you can see it's a bit larger network or a medium network structure. If, for example, the central node would here fail, the network would again break down into subparts, but the rest of the network is still quite resilient against failures. That's why we obtain all these measures. And now to recapture what we did and what we achieved so far. So we made a realistic pilot where we characterized the resilience of a network of reasonable complexity with a quantum computer. So the model that we studied, as Antonio already said, contains in total about 150 variables, which is roughly 10% of the size of an actual network. So if we now look at the roadmap of our partner QuEra here, we see that 10,000 qubits will be available in 2026, where we believe that if we can use this number of qubits, we expect to approach quantum usefulness also for real network structures. So therefore, we now tackle the problem of significant size and significant complexity, even on today's hardware, without error correction, which means the error correction is for sure helpful, but may not strictly be required to demonstrate usefulness even on near-term machines. What does this now mean for the telco and energy sector? So we have shown that we can tackle decent sub-problems in networks optimization and see a path towards advantage with the upcoming hardware devices. When we can solve these problems at scale, we can improve the network performance, resulting in a boost of customer experience, for example, being a very low downtime, or even we can avoid downtime completely in these systems. We can also increase the operational efficiency by identifying unnecessary redundancy. For sure, redundancy is really important in the network, but just adding more redundancy is also very costly. So therefore, we want to avoid unnecessary redundancy. This also means that now it's the time to move, especially with the 10,000 qubits expected in 2026. Before, I would also like to use the last minutes I have to explain a bit more what we do in addition. So we are also working on digital compression. So this means we're having algorithms that also use very similar techniques, so counter-diabetic terms, to compress digital systems that we then also make application specific. And we are there looking really forward to also explore our algorithms on the new digital hardware of QuEra. What we now explained to you was the analog compression, where we combine analog blocks. And then we also do the combination of digital plus analog, where we then do, let's say, digital gates plus analog blocks. So we combine the best of both worlds. And I would highlight a bit more here the analog compression, since we very recently published there a paper on Friday about also recent results that we obtained there. So what we did there is we developed an algorithm using our counter-diabetic methods. And this algorithm has a higher success probability and approximation ratio than standard adiabatic evolution, which results in a faster time to solution and an improved of the solution quality. So we tested these things on simulations, but also on the real hardware of QuEra on the cloud. And what we also find here is that this algorithm that we're developing has applications, for example, also in the sampling of distributions. As you can see here, our ACQC algorithm shifts the distribution of states to the left, while requiring, for example, no hybrid overhead. So therefore, we can use less number of shots to sample higher quality solutions, and therefore reducing the overall time to solution. We also believe that our ACQC algorithm that we developed paves the way to near-term advantage with analog computers for certain optimization problems. The steps we are taking is to adapt also our algorithm to the next generation of devices, like adding the local detuning feature of the QuEra devices. And we believe that when we can start solving real-world problems with 150 qubits plus, we will heavily approach the quantum advantage. And if you got interested and would like to get more information, please reach out to me via email. And for example, if you also would like to get the link to the paper, and we're also very happy if you would like to engage with us, for example, test our algorithm libraries or work on a showcase with us or develop a key concrete pilot, very similar to like that Maslow did with us. Thanks a lot.
Thank you, Jan. And a couple of questions came while you were discussing. Jonathan, perhaps first to you. Jan mentioned the concept of gadgets. What is a gadget, if you could explain briefly, and why are gadgets helpful in this case?
Yeah, this is a great question. So a gadget probably has a better technical definition than I'll give here. Basically, it is a certain structure that equivalently does the same thing as another structure. So for example, a gadget in our context might be some subset of atoms, like some subset of positions of atoms, whose ground states or maximum dependent sets of that substructure represent the equivalent maximum dependent set of some other subgraph. And the idea here is you can take any non-MIS subgraph and turn it into an MIS subgraph using these gadgets. The concept, of course, extends well beyond this to things like circuits as well, but at least in this case, this is this sort of mapping from one kind of graph structure to another graph structure.
Excellent, thank you. The next question is for Antonia, perhaps. We've seen the concept of network resiliency or a resiliency measure of a solution. Would you consider this type of solution to be helpful in designing upgrades to the network? So for instance, where would connectivity between nodes need to be added to increase the network resiliency?
That's a good idea. Every year, network engineers plan enhancements to the network, and if they have a way to assess the increase in redundancy beyond the obvious things that they have in the design graph, I think they will be interested in having that assessment beforehand.
Excellent. And Jan, how does this solution scale? So let's assume you started with, I think, 42 or 46 nodes, and you were able to fit them or some version of them onto the quantum computer. If you now had twice the number of nodes, do you need the computer that just has twice the number of qubits, or does it scale non-linearly?
This strongly depends on the problem and on the connectivity. Here, for example, we model a backbone. We only needed a slight overhead, so like a factor of 2. But for sure, if we, for example, get then a more dense backbone, we also expect a more denser overhead we needed to just model the connectivity. So very similar, we would need, let's say, more gadgets to reflect the full connectivity in the system.
Excellent. And Jan, another question to you. What was the main challenge in building this solution, and what surprised you the most? So as you were at the end of building the solution, what did you say, oh, I didn't know that was going to happen this way, and this is something that you felt surprised by?
So one thing was actually to somehow model the problem in a way that we could fit it on the device in a nice kind of way, so that we could extract solutions and vice versa, and to model it back. So the post processing was actually also not that trivial, because when you have to sketch it, you then have to check if your final solution is still a valid one, or if you just got a solution of now you gadget things, but this does not follow the boundary conditions of the actual solution. So this was quite surprising, and this also was kind of a bit of a challenge that we had to do.
Jonathan, maybe a question to you. Are there classical approaches to solving MIS problems, and how do they compare to quantum? At what point does quantum truly deliver an advantage?
Yes. So there are a plethora of classical optimizers to solve these sorts of problems. And I would describe the situation sort of as follows. The classical community has had 50 years to develop algorithms that are like really good, and we've had, say, 10 years to develop similar things. To this regard, there are many different options, everything from, say, greedy algorithms to branch and bound algorithms to simulated annealing algorithms. But typically the strategies here are heuristic, which means it's sort of a educated guess and check, and you don't necessarily get optimal solutions. And this might be where a quantum device, especially in integration with these sorts of classical algorithms, might actually be able to outperform the performance of either on its own.
There's a question that perhaps I could answer. The question was, where, or are the biggest technical challenges in building and maintaining Aquila? So I think first, it's always challenging to build something that's first in the world. And Aquila is the first and still the only publicly accessible neutral atom computer. So there have definitely been demonstrations of neutral atom computers at university labs, and we enjoyed the fruit of many of these demonstrations. But it's one thing to have a university demonstration, and another thing to have a service that consistently runs 130 hours a week, meets the stringent service level agreement requirements of AWS in this case, and make sure that customers can indeed get value of it. So this, I think, is a testament to both the ingenuity and the hard work of our team that worked nights and weekends to be able to deliver that. And I think the last question, again, on sort of comparing classical to quantum, Jonathan, aren't most classical algorithms for optimization basically best guess? And so is there sort of a more systematic, algorithmic way to come up with a quantum solution for an optimization problem?
Yeah, this is a great, yes. So I guess there are two options. One is this sort of guess and check method, which is what you just described. And then the other is like an exhaustive search, right? And the best guess, right, which could be an educated best guess, right, might happen to find the optimal solution, and possibly, depending on the algorithm, such as branch and bound, it might sort of be a best guess exhaustive search, right? But then on the other side, it's the exhaustive search, where you just try every possible scenario and then just, say, okay, after some possibly exponential time, you actually converge on that solution. But typically, because these problems are encodable into NP-complete problems, this means that the overhead in order to find these solutions is also exponentially large.
And I think we also had solutions in customer projects where we had very, very good initial guess using the quantum computer, and then did fine-tuning in post-processing classically.
Exactly.
Tonio, a question for you, please. One is, how satisfied were you with the outcome of the project, and what, if anything, does CINFO intend to do next using quantum computing?
Well, we were very satisfied with the collaboration, with the modeling, with the defining of the toy model and everything. And of course, our plan is to evolve this initial step into a full production system. We know that we have to keep the project live, updating the network model every year until we reach a delivery that can be useful for network engineers. We selected Kipu because we had collaborated in a prior project with them locally here in Galicia, and our plan is, well, to extend this kind of concepts and algorithms, not only for telco networks, but for energy and also for logistic scenarios.
And did your team have already had deep experience in quantum computing? Did you have a team that was learning and running quantum programs for several years, or did you primarily rely on the expertise of the Kipu team?
No, well, I'm physicist myself, but I don't know nothing on quantum programming. I'm just interested. We have a research and innovation unit with some people fluent on quantum concepts, and we also hired a couple of quantum developers, but we consider ourselves really as the interface between the customer and a full expert like Kipu. You know, network engineers in a big telco, they know nothing about quantum computing. They even don't care about how to map the network to the quantum architecture, but they are very interested in the quantum assessment on the resiliency of the network. So our job is there to intermediate between the quantum experts and the customer.
Wonderful. So with that, I think it's time to close. Antonio, Jan, Jonathan, thank you so much. And of course, thank you for the audience for participating. And we look forward to seeing you in our next event.
Okay. Thank you. Bye.